when my previous company got acquired by Mellanox, I suddenly got exposed to this huge supercomputing industry and so many computing platforms other than CPU. I mean, it was back in the days. GPUs, just one vertical, FPGAs and more. And then I started to think, okay, how can I reimagine compute?
Welcome to AI with Sally, an EE Times podcast that brings you inside my conversations with luminaries of the AI chip industry. Up to now in computing, if you wanted better performance, you had to rewrite your software to fit the hardware. But what if we've been doing it backwards? My guest today, Elad Raz, is the co-founder and CEO of NextSilicon, a startup that's building a novel kind of processor that can reconfigure itself in real time to match whatever code it's running. So instead of forcing you to optimize for GPUs or CPU, NextSilicon's approach uses runtime telemetry to adapt the silicon on the fly, targeting a small fraction of code that actually dominates execution. In this conversation, I'm asking Elad how that works, how we can apply it to AI, and what about that RISC-V CPU the company developed? Here's my conversation with Elad. Hi Elad, welcome to the show.
Hey Sally, thank you for having me.
Of course. Perhaps we could start by just telling the audience a little bit about NextSilicon. I know you're the founder of the company. How did the company start, and kind of what was your original thesis when you started the company?
Sure. So let's start with me. I'm a software engineer. I'm a geek. I'm a nerd. I like to create. I wrote a lot of code, optimize inline assembly back in the days. And I started my own company that Mellanox acquired. And in that company specifically, we did a lot of low-level networking optimization and high-performance computing. And when my previous company got acquired by Mellanox, I suddenly got exposed to this huge supercomputing industry and so many computing platforms other than CPU. I mean, it was back in the days. GPUs, just one vertical, FPGAs and more. And then I started to think, okay, how can I reimagine compute? And it all starts with the little details. And from that 3 years at Mellanox, I just watched the industry and I say, what if we can do things differently? Hence, the creation of NextSilicon.
So what was your original idea for doing things differently?
Well, very similar to what the company does today. It took me almost as an engineer. I remember that I've done the first fundraising, okay? So imagine me just starting the company, going to an investor meetings, which I don't know how many in your audience have ever spoke with investors. Some of them are highly sophisticated, but most of them are journalist investors. And I start talking about reconfigurable hardware and compute and computation graph and LLVM and so it took me hard to articulate what we are doing in high-level general way into more of low-level things that I think your audience are like me. So I'm so much pleased that we can get to the guts and the details rather than staying at high level. So I've been just toying with FPGAs. And FPGAs are data flow with a lookup table that you take a compute graph and place them on the hardware. And there was, at the time, a lot of companies doing high-level synthesis. High-level synthesis means, let's take a C code, for example, and try to do the synthesis and place and route from a C code. And I don't know how many have played with those tools, but it's like painful to watch. And then I try to say, well, why it's so bad? And then the answer is that everything happens statically at compilation. Like you give the synthesizer a C code, it take it, crunch it, and just guess how the output should be. Never works. And then you need to go back and add intrinsic into the C. Intrinsic is just annotation to the inside the C code, and and I remember there was a company called Metrionics, and you had the Metrionics C, that it's a different variant, like domain-specific language for FPGA. And the key insight is, well, statically, it will never work. What if, you will do the high-level synthesize, read from the FPGA some telemetry point, and then go to the drawing board and re-synthesize. So that was like the inception point of the algorithm. From there, things got escalate kind of quickly.
Okay. So reconfigurability, but not static. What does that actually look like? How have you actually used that idea in hardware?
Yeah, so everything. Just at the beginning, I thought, okay, let's not raise $150 million. Do you know how much it's painful to raise $150 million? That's like the money you need until you get samples into the market. So many investor meetings. And I thought, okay, let's take an FPGA, reconfigure it, and then reconfigure it, and then I figured out that none of the Altair and Xilinx supports reconfigurable. I mean, you literally need to run 8-hour full synthesis and then a power cycle. So whatever the first day of the innovation, the second day I already discounted FPGA and I say, let's do that. Let's build a hardware chip. And it's got this. Nothing at NextSilicon in our architecture looks like an FPGA. So data flow, it's a term that is misused often, but when you look at industry data flow, you have the different primitive or the ALUs, the different math function themselves, just in an array. No execution unit. No instruction fetch unit, no bridge prediction, none of that exists. I mean, and it's funny, but I'm trying to highlight this idea that, NextSilicon is a sea of values, it's not a processor core, and then people say, well, that's VLIW. No, like VLIW is when you have an instruction and a processor core read instruction. Just the instruction has a lot of different words of operations. No, this is just a compute graph. You etch it at block of ALUs, and data is moving north to south. Literally, that's it. That's data flow. Removing 98% overhead of GPUs, CPUs, processor core like the SM or the x86 block. Just keep the ALUs and flowing back. Let me give you another example at Los Alamos. Back in the days when Manhattan Project was in order, you had to run a lot of computation. So they took a classroom and they put people, who most of them were women, to do calculation. Each one of them did just 1 or 2 operations, take the paper, move it back to the next table to run its own pipeline of operation. That's a data flow. Super hard to program, okay, by the way. It's extremely hard to take your whatever algorithm that you want to create and build a data flow graph. So how you are dealing with that? I mean, many companies have tried to build a data flow processor core. What is so unique about NextSilicon? Going back to the original idea, the runtime part. Okay, you don't have to guess it. I mean, put a graph in, get telemetry, get information on the graph, and place it on the hardware. The nice thing about runtime is that no one thought about it. Not in academia, not in industry. I mean, before us, the market had only 2 approaches to go with novel compute architecture. The first one is, let's build this, best-in-class compiler. They're going to read everything, know the underlying hardware exactly, and we are going to guess exactly how to schedule the instruction into the processor pipeline that will be like this majestic kind of work. I don't think that a single company, starting from Intel, the Itanium processor, were able to make it happen, or the Itanic. So that was the first approach. The second approach was, hey, dear customer, here is my chip. That's the most powerful chip out there. But you have to study it. You need to understand the microarchitecture of that processor core. You need to know which instruction you should use. You need to understand the caches, the cache sizes, when there's going to be instruction cache miss, and when there is a data miss or data cache misalign, and fix your code and use always vectorize, so there will not be any stall on the pipeline, and then you can maximize the performance and it's going to be wonderful. Only one company were able to succeed in that, and that's obviously NVIDIA with the CUDA. And there is lots of reason why everyone failed, but if you think about it, it just generates such high friction between the customer and the vendor. Because the customer, even if the customer will tell the vendor, hey, just here is my algorithm, just rewrite the code, and the vendor will do that and show wonderful performance, then but this code will be unmaintainable, okay? So there is like a fresh, and I think that NVIDIA is a master class on how to do domain-specific language, but the pain point of being a vendor lock and then paying the price that GPU's prices, I don't even want to say triple, because I think that Hopper are selling now 5x than their original prices, or something like that. Correct me if I'm wrong. Yeah, it's crazy.
I've heard some crazy figures, yeah.
Yeah. I got like a second-hand suggestion on a server with Hopper, and I say, how much this server cost? And say, I would, yeah, just crazy. So we have taken the third approach. Okay, runtime. Use your own code. Very hard to program our chip. I'm not going to sell you this majestic compiler that going to understand everything in advance. And yes, I'm going to guess wrong. So at the beginning, you will see a bit of less performance, but as time goes, I will learn your application better way and literally reconfigure the ALUs. It's not a lookup table like an FPGA. It's like an ALUs and configure them the right way. So that's the geeky explanation about what NextSilicon is.
Let's get a little geekier, if you don't mind, because I'm very curious if you can tell me anything about how the telemetry actually works. Like, how do you decide when to do the reconfiguration and how to reconfigure?
Are you sure that we are going to derail this conversation?
Yeah, I want to know.
Okay, I was sure that you're going to tell me, let's get it one level up. But yeah, happy to do that. Yeah, so telemetry and data flow, and it's so there are just few people on planet Earth that really understand compute. So I will try to explain it in high level, and then we'll go better. To start with, data flow has no branches. I mean, if you have, let's take Monte Carlo simulation. Monte Carlo is when you go over all the different options, you have different type cases. And GPU specifically have a single instruction at any time. I mean, yes, they did some optimization there. But if you have a lot of branches, then GPU, they don't have just a deep branch prediction pipeline and queues as a CPU, so they are getting lost, and every branch miss is very painful. In data flow, you just take all the different cases, put them on the silicon, just literally execute them on parallel. You put a condition on memory whether this memory operation should happen or not, because you don't want to waste like memory and network on chip resources on cases that doesn't happen. But you just run everything, and then you have a selector in LLVM. It's called like phi operation that select just the right condition that happen. So you run everything on parallel. Great. The problem with putting your entire application on a single chip is then the data flow become like huge and chunky. But you have some cases that you can literally separate and then make the graph smaller. And it's all about throughput, how you can push more compute. Here is another example. If you have a for loop, and you always have the same parameter, same variable on the matrix's size or other constants inside the graph, specialize that, learn that. Just say, this is like tensor of 16K by 4K, etch those numbers, unroll them exactly to those numbers without any left. I mean, the problem with unroll, when you take a loop, unroll is a CPU transformation, that you take a for loop, and instead of doing it by one by one, you can just unroll it by 2 or by 4, and then things became not serial, but like more parallelized because you have, and memory is getting coalesced. Great, okay? What happened at the end? So suddenly at the end, if the number of iteration is, let's say you unroll by 4, if the number of iteration is not divided by 4, then you have a leftover that you need to take care of, and the compiler generates you this piece of code. But if you know exactly, it's always going to be a multiplication of 4 or 6, you can have a specialized kernel just doing that. Okay? And this is one example. I think that most of our specialized code and data flow is amazing if you have a lot of data. If you have a lot of data to crunch, the one thing that you want to put is put the compute and then start feeding data inside the graph. Feeding. Great. Most of the optimization is around that, how to open those bottlenecks, how to change the code so data can stream. And in the last supercomputer, we had the giveaways of a battle opener, and we made them in the shape of our PCI card, and we call it bottleneck opener.
Love it. Yeah, very good. What did you actually have to invent to make this happen? I know you said you don't have a majestic compiler that does everything at the start, but you must have had, there must be some significant software behind this as well, right?
Everything. We had to invent everything beside LLVM, right?
Okay.
And MLIR.
Yeah.
The compiler from scratch. And obviously the entire hardware. And we had the Maverick 1 and Maverick 2, and Maverick 1 was kind of a test chip, and many insights and technical insight. I mean, the jump between Maverick 1 and Maverick 2 was huge because I would try to throw it as a sentence, giving you a scoop. I'm going to publish a paper about that. But the problem with data flow, is when you get to the memory point, when you need to go to the memory, everything becomes bottleneck. So everything is flowing. You go to the memory, suddenly one memory load operation get installed because the data is page out on the disk. You need to fetch the page, and everything got stalled. Okay? And in MAV2, we figure out a way to take a register file, we call it reservation station, and how to take care of those cases that threads will schedule out of order. Neat idea. It's a patent, I have to say that, so people can read it. Probably they won't understand much, but we are going to discover that. So lots of innovation in computing platform and data flow, not just the network, the memory, the virtual pages, and translation look-aside buffer. I mean, so many operations there. And obviously, the set of optimization that we are doing are not static compiler CPU-oriented. Those are MLIR passes aimed to optimize compute graph on data flow. We have an amazing team in Zurich that doing those optimization. Like, it's a magic what those guys are able to achieve. So, very proud of what we have done so far. So yes, we had to invent almost everything. Remind me that the next startup I will take like an easier kind of a challenge, trying to reinvent everything.
So one of your biggest claims, I think, is that you can run any kind of code out of the box. So I know your biggest market is HPC. So in scientific computing, you got C++, you got Fortran, you got all sorts of crazy stuff. You got legacy code. I know you do a lot of work on software, but what is it about your stack that makes that any kind of code possible?
Well, let's break it down. There are things that we are doing badly. And data flow, and I said in the beginning, is when you have a lot of data to crunch. You have like set of X algorithms. I don't care how much because the data reconfigure itself, so there is no limitation on size. But if you can take a data flow and then start feeding a lot of data, amazing choice. Sometimes in HPC, not necessarily in AI, you have parallel region that you feed a lot of data and then like a serial kind of a join or a reduction, which is highly serialized and you cannot parallelize it because that's the way that the code is being written. And if you will try to run it on the data flow, it's going to be painful, okay? But in order to achieve that, we are not dissing CPUs. CPUs are amazing. Okay? And CPUs are best to run serial code. So why not combining both? And I remember this point where I sat down with Ilan, the VP architecture, in a room, and I say, well, data flow is great. And like in the beginning, we said, okay, let's take the serial code and put it in, but Fortran code, and you have trilinears, you need to put the entire software. It's just huge. There is no way it can fit a 100 billion transistor an accelerator like the Maverick 2, and then we said, okay, let's put like a CPU next to it, ARM or RISC-V, and let's schedule the code where it fits. The job is not to go, GPUs, and probably your audience are geeky enough to know that, you go over the PCIe river. Okay, you need to cross that river over PCIe, which take huge amount of time. You go from the PCE to the application, run the code, and then you launch a kernel, and then you have so many tricks on how to optimize kernel launch time. Stay at the accelerator, stay at the device, and stay at the Maverick chip. So we put, at the edges of the chip, we put RISC-V cores, our own design, and then we said, okay, when you get to the serial code, execute it there. When you go to the data flow, run on the main chip. So this is where they work badly. Another thing that, missing out of the box, can run everything, you can always run the code in a better way. And if you have a shitty algorithm that is written for a CPU that has only 4 levels of parallelism, that's it. 4 cores, and then the reduction is so much painful, I won't be able to help you much.
Okay.
So those are the two things that I'm getting a lot of questions asked, and that's about that.
Yeah. Can you even run CUDA code if somebody's listening to this thinking, I don't believe you can run any code? If I have loads of CUDA code, can you run that too?
Yeah, absolutely. Yes, drop-in replacement. And obviously, we are using the LLVM front end of CUDA. Okay, we are trying it's illegal to do anything with the PTX level. So if you give me a binary, I'm not going to run that. And CUDA framework is kind of a ever-chasing race. Luckily for us, AMD has a ROCm stack, and they put in millions of resources on doing that, combining the two, because the language doesn't detect what we are doing. With CUDA specifically, you have sync threads, and you have barrier, and you have shufflers that mean a couple of threads or block how to move them around. We have some limitation on Maverick 2 to run the shuffler in high performance, but we are fixing them as things move forward. But it doesn't matter, it's just a few operation extra. But yes.
The overall aim is performance, is to speed everything up. It's not just flexibility. And when you say flexibility to run any code and performance kind of in the same sentence, that's where I think people start to, I'm like, I don't believe you. Are we really trading off flexibility with can you really achieve both the flexibility to run any code and performance at the same time? It's, I think, what people are probably thinking.
They're right. I mean, they are absolutely right. You can take the code, run it on Maverick, get a performance number, see that, look at the profiler, and then say, okay, now I get it. Those modifications can speed it up way faster.
Yeah.
I never said out of the box you will get the max possible performance for this algorithm. Never said that. I say you will get the performance. You will get better CPU or GPU depending how your code is being written, and you're going to get acceleration. Otherwise, it's a bug. Because just to start with, if I see there is zero parallelism, let's keep it on the CPU level, not migrate everything. So that's 1x. But you will immediately see there is no parallelism. You know, our entire toolchain will say, "You're an idiot," in a nice way.
Okay.
So yes, absolutely right.
Are the advantages limited to people who already have code or who are already running code, legacy code or relatively new code? Is there an advantage that I can get for writing specifically for your hardware?
Yeah. Customer acquisition is hard and painful, and telling a customer, here is my hardware, now take the entire code base that you've been running on supercomputer for the past 20 years and just port it to me because I have such a wonderful smile and I can make coffee, won't sell it. But telling them, look, here's the Maverick, take your code, start running them, measure that in small scale is a lower friction point. And let's talk about AI workloads. In AI, you know everything in advance, okay? Whether you are doing training or the prefill phase or the decode, you get the graph. In PyTorch, you have the Dynamo that run the Python and then build the computational graph. You have Iris tag that know how to do kernel fusion if needed. Like, you know everything in advance. So that's it. Data flow has no meaning over there. Obviously, in AI, there is no point of getting the telemetry because either you have a bug and you place the memory far away from the compute, and if you put it the right way, those are massive tensor that you can parallelize, and you can do tensor parallelism and lots of cool things. But this is where people get it wrong. Data flow is not just about the computation, or other will say, well, decode with batch size 1 is equal to the memory bandwidth. Because if I have 70 billion parameter and my memory movement, I'm just doing it simple, is 700 gigabyte per second, let's take FP8, it means 10 tokens per second to generate. That's like the overall on transformers. So there is no way that your architecture will be better. I can just read your memory bandwidth and get estimation about hardware utilization. But they discount power consumption. They discount the fact that I remove 98% of the pipeline of the SM and made everything so simple and so tiny. They discount the fact that when you're doing batching in AI, some of the pipeline like the attention and KV cache, you can't batch. It's a serial code per user. But the FFN, it's something that you can batch, and when you batch, you can leverage the memory bandwidth. And here is the last point that I want to say about that. Thinking that transformers will stay the same and nothing is going to move, and there is going to be GPT-11 that's going to look exactly the same, so we can build a chip dedicated only for transformers, is not the right way to go. We still have 1000x on performance on transformers, and this 1000x number that I'm quoting is because today's LLM takes 20 kilowatt to run an operation that our human brain can do in 20 watt. That's the 1000, and it's not going to 0.01 nanometer in the transistors or building them up. It will be an algorithm. And even now, Google, last week, Google announced a new paper that's called TurboQuant. It's a way to compress the KV cache, the serial code, and then they demonstrate how they can get on the same memory bandwidth 8x more because it's 8x compressed. Great. Can I run those kernels if I have fixed place SRAM to put the KV cache and that's it? Not necessarily. So yes, general purpose always wins, period. Allowing the user to bring your own MLOps, your own code, always win. Do you remember that we used to have a Sound Blaster card back on the days? Yeah, I mean, dedicated processor doing audio. CPUs became better, we are doing things way better than needed an audio coprocessor. That's just life.
Because we are seeing this trend in big commercial deployments, disaggregating, splitting prefill from decode, more specialized hardware kind of coming in. I understand your points about being a general purpose accelerator, but do you think disaggregation helps you because it means you can take bits of that market from NVIDIA?
So it's way easier to go to a niche market than staying in the main one. And when I say the main one is put the question about prefill, yes or no, because at the end of the day, prefill is operation that is matrix multiplication dominate, and then you need more computation than memory bandwidth. So why go to advanced packaging? Why go and put an HBM that is super expensive? Let's take a DDR and can get similar results, because if you will put an HBM, the HBM will stay idle at the prefill phase, unless you're doing a crazy batching of 256 queries. Good. But this is some of the area. But you're absolutely right that even at AI workloads, you have many different applications. You have small models, which are typically voice to audio to text, or diffusion models to generate images. They are tiny. Why do we need 288 gigabyte of HBM for that? Let's buy a cheap accelerator sub $1,000. Performance per power per dollar makes sense, okay? So yes, they have their place in the world. If you ask me, the majority of AI workloads in the inference, in the decode phase, is around the big models, the 2 trillion parameters, mixture of expert, with 1 million context window. That's like the majority of the workload, and there is no way to run away from an HBM. Period. Yeah. You need that. And another niche is, and this market, someone put a $20 billion price tag on that, like SRAM fast inference. Well, yes, I can put lots of small chip, inexpensive one, SRAM, lots of memory bandwidth. I think that for a trillion parameter, you need 2,000 of them around. Great. And yes, you can run faster. But will user agree to pay 10x more dollar for a model that runs 3x faster or not? I'm not sure that market have proven it yet. Obviously interesting, but again, that's another segment that specialized chip can come into play. So absolutely.
Yeah. I know you're working on something more specifically tailored for AI in the next gen. I assume it's going to be lower precision, will be one of the differences, but can you tell us anything about what you're working on AI-wise, and when is that coming?
It's coming. And,
okay.
So let's talk a little bit about AI. Maverick 2 is here. It has FP64. It has incredible memory bandwidth. And we are doing demos on AI even as we speak, because if the weights and the KV caching is in the HBM, you can prove your entire nuance. And for us, going and have a product that has the smaller precision and is just the next evolution. Support HPC, keep the FP64, add the lower precision, serve both markets in this mixed way that you need to support HPC and prefill and decode kind of a way. It's exciting journey for us, and way more announcements coming soon.
One more thing I kind of want to ask you about, which is this CPU that you've made. You're also making a CPU. I understand this is going to be a RISC-V host CPU. It's going to be quite a big CPU to go alongside your accelerator. Why? This is really difficult to do. Why not just buy one, Elad?
Well, remember that at the beginning I said that I'm an engineer. And as most of the engineers, we hate ourselves. And joke aside. At the beginning of the company, when me and Elon sat down and said, let's put a processor core next to the data flow itself, we had big debate whether we should use ARM. And we almost took like ARM license and just put it on our Maverick. And then Jensen decided to buy ARM.
Right, yeah.
And then
it didn't happen. But yes, it looked like it was going to there for a minute, yeah.
But either way, whether it would happen or, the unwinding from this NVIDIA agreement was painful. Yes, it was a long time ago, but it was painful, and we wanted someone who give us an attention. Yeah. We want to have the ability, for example, to change to support far atomic. Imagine that the grid wants to do schedule atomic operation. It needs to go to the RISC-V. The RISC-V need to understand that this is atomic operation coming from an accelerator, and ARM didn't support that at the time. So we took a vendor for the Maverick One, and in parallel we said, well, it's hard. And how hard can it be? We just need little core, okay? We don't need someone sophisticated. And luckily, we hired a brilliant guy, Iftach Gilad. But this amazing group of people, him and Liron Tzur and Eyal and other, like a group of people that literally build processor core. That's what they have done in the past 30 years. That's what they know. And they say, let us take care of that. And we said, okay, let's start with this little core, the concept of a small core that doing that. And then they say, well, Elad, we can do both, like in parameters and sophisticated place and routes. So me as the CEO, well, if it doesn't cost us much, let's do that. Let's go for that. So we have it. We have another, we tap out the chip and we got it back from TSMC a few months ago. That's the Arbel chip. It's tiny compared to the big one.
Yeah.
This is an interesting chip, but we'll tell you more next time. So yes, we got it in silicon. That's literally the best RISC-V out there, period, in silicon, in performance, period. And based on that, we have seen a lot of demand, way more than, when we did the launch in October, it was supposed to be all about the Maverick 2, about the grid, about the data flow, about educating the market. And, the chip just came, and I said, why not? Let's just say one more thing. Here's the RISC-V. And we got almost equal coverage between the data flow processor and this RISC-V processor core. Lots of market demand. And,
Is the market demand coming from people who want to put them alongside AI accelerators? That's what it's designed for, AI kind of accelerator host, right?
I think that for us as NextSilicon, let's be honest. RISC-V is far away from fully being in market maturity, and software and Linux and framework is far away. I don't think it's going to be painful as ARM have done, like for 15 years, getting this adoption from a processor until getting into mainstream. I think it's going to be shorter, and I don't think that the timing to the market is now. So if you think about it, who wants to buy a host processor core? Answer: sovereign data centers that have a specific workload and they are more cost sensitive, that you can go after that. Or just reducing the total cost of ownership for your own rack that you're selling to customer, because at the end of the day, those are computational nodes that just run one function on the PyTorch stack and drive the Maverick. So, okay. Here you go.
Because I think we are seeing more interest in CPU, or certainly a lot of attention on CPUs as we move towards agentic AI. It's kind of the reason I asked the question. ARM just released this, big CPU that it's making for agentic to handle that part of the workload. So I'm curious about whether that would be maybe a future market for you.
We'll see.
Okay, well, I think that's a great place to leave it. Thank you so much, Elad. Really enjoyed the chat, and we'll be watching out for that new gen AI accelerator when that comes.
Yeah, it was my pleasure, to go fully geek on 100%. So thank you for this opportunity, Sally.
Anytime. That brings us to the end of the episode. Please tune in again next time for more conversations around AI silicon and systems. If you're listening to this on the podcast page at eatimes.com, links to articles and topics we've discussed are shown on your left. AI with Sally is brought to you by Ask and Core Media. Thank you so much for listening.